put a 1 here. So now this trie has the word code in it. And for the word coding, you would go to the C, then to the O, then to the D. Then you'd go to I, which, yeah?
So we can write like bigger?
Oh yeah, I can just zoom in. Yeah. Better? Okay. So then after you'd get to the D pointer here, and then you'd go to I. What letter is I? F, G, H, I. So it'd be 8. And then you'd go to N, and you go to G. And you'd put the 1 there. That makes sense? And each one of these individual nodes have 26 child pointers. It's just most of them are null.
Okay.
Yeah.
So that's the like diagram up there where it just has like the letters and then the lines, and then like each level is like its own segment. Is that an acceptable way of writing it?
Yeah, you can write it that way. You mean like when he has it goes down and then it goes like to the left?
Yeah.
Of that pointer? Yeah, that's another way of writing it.
So like the top would be the root, and then that would be the
Right, this would be root.
height one where your A and C would be, and then after that it would be like an O and P.
Right, right.
Okay.
Yep.
For the exam, would it consistently notate the 26 child pointers?
No. You don't have to draw 16 child pointers. Like just how I did here, how I didn't write the other 25, you're not going to have to write the other 25. You're good. Any other question about this? Yeah.
So we always have to write numbers instead of letters. Like for example, A is 0.
Generally you do. You write the number.
Okay.
Yeah. So there's going to be one more example of it here that I'll let you guys work out first. Okay, so to start with Minheaps, a Minheap is a type of binary tree that is always complete. And when it says complete, that means it's filled up from the highest node to the lowest one. And on the lowest level, it's filled up from left to right. So I'll show you an example of that. So if you have this example here, if you have this tree right here, this tree would not be complete because even though it's filled up until the last one, it doesn't start from the left to the right. If instead of that you had this here, if you had this here, this would be complete because it's filled up from left to right. So one property that min heaps and max heaps both have is that they always stay complete. So in this case, you would start with 27, which is here. And then to input 8, in order for this to stay complete, you would have to put it at the leftmost pointer. So the 8 would have to go here. And then after you put in a new node, then you move it up until the node above it is smaller than it. So in this case, you would move this, you would switch these two, and then it would become this. That way it stays a min heap and it's still complete. So then when you put in 15 here, you input this here and it doesn't move up because 8 is already smaller than it. So then you would put 30 in here, and that would be fine there, and then you'd put 42 into the next pointer. And that also works out, and then when you put 28 here, that also works, and then 40 here. So say, for example, we wanted to also input the number 7 afterwards. Then we would put the 7 into the next pointer. And then since 7 is less than 30, these two would switch. And then 7 would be here, and then these two would also switch, and then they would switch with the 8. So then you'd have 7 at the top, and then 8, then 27, and then 30. Make sense?
I have a question.
Yep.
So unlike a binary tree, when it inserts the second value, it just goes to the left, it's empty.
What do you mean?
So in a binary tree, if you had an 8
Right.
and then you put in a 27, it would go to the right, but you drew it to the left.
Right,
You
so,
put it to the most empty leftmost one.
right, so it's not all binary trees where it would go to the left. That's AVL trees you're thinking of, or search trees that you're thinking of. In search trees, the node to the right is always going to be bigger than it, and to the left, it's going to be less than it. This doesn't have that property. The nodes to the left and the right can be less than, or, I mean, they both have to be bigger than the node itself. So like, if this 7 is here, this could be the 15, and this could be the 8.
Okay, so for testing purposes,
Right.
it's not particular what side you put the 27 on. If you put the 27 on the right, and then you put the 15 on the left, it would be equivalent.
Right, so if this was 15 here, and this one here was 8, it would still be correct, because it keeps the properties where every node's children are greater than it.
Yeah. I was just wondering, like, if you asked a test question, and like you flipped,
Yeah.
the same order,
Yeah,
you flipped the two, and it didn't mess it up, you get a wrong average.
okay.
Okay.
But like, if I were to switch these two, then it wouldn't work, because then 30. Yeah, 30 would have to move also. So the next step would be to delete from the min heap. So from these here, one thing you have to realize about min heaps is that you cannot delete a specific node. You can only delete the node on top. So in, let's say, I'm just going to rewrite the tree down here. 27. Let me put 15. Okay. So if we had this tree here, and we wanted to delete twice from it, first we would delete the 8 here. And then once you delete the root, you take the largest number from the left subtree. So in this case, you would go to the left subtree, and the largest number is 42. So then that would become the new root. That would be 42. Doesn't have one. And then after you move that to the root, you would move it down until there's nothing that's bigger than it.
Why is it 42 again?
You take the largest number in the left subtree.
Largest number in the left side.
Right. You do that because this node, the largest number in the left subtree, is guaranteed to not have a right pointer. Because if this were to have a right child, then that would be the greatest, and you'd be switching that instead. So you would move this to the root here, and then just to make sure that it keeps the properties of a min heap, you would move it down until there are none that are bigger than it. And if both of, or none that are smaller than it, sorry. But, so in this case, when they're both smaller, you switch it with the one that's greater. So in this case, you'd switch it with the 27 here. And then 27, 42, 30, what am I doing? And then once you get to this one, you would, this is still smaller, so you'd switch these two. I'll give you 27, 30. Okay. Oh, wait, no. You were supposed to switch it with the one that's smaller, sorry. So, like in this case, it wouldn't work because the 27 is larger than the 15. That's why you have to switch it with the smaller one. I made a mistake and switched it with the larger one. Okay, so in this case here, you would switch this with the 15, not the 27. Okay.
So it compares to the left and right, and then just switches with
Right.
the one that's smaller?
Right.
Okay.
Unless neither of them are smaller than it, then it would stay where it is.
Okay.
So then this would also switch with the smaller of the two, which is the 28. Then you have 15. Okay. That makes sense? Yep.
Is it possible for a parent to have more than 2 children?
What do you mean for a parent node to have more than 2 children? You mean like here?
So, any node that has children always has 2 in the examples.
Right.
To have more than 2, 3.
No, because a min heap is a binary tree, and binary trees can only have at most 2 nodes.
I have another
Yep.
question. So, shouldn't this tree look incomplete because it's missing like one of the left side, one of the right side of the left from 15? Because you know how like
Where?
the tree should always be filled up from the leftmost first.
What? Oh, yeah. Yeah, I see what you're saying. Not sure. This is another time where you can go to that same website I showed you before. It also has heaps. So I can show you how it would do the heap here. I can create it and show you if this would work. Oops. Short. One second. Yeah. One sec. Do you know how to make the computer show up on here? Yeah, so I pressed this to go to the computer, but it's not showing on the screen. I don't know why.
both sides.
Okay.
Both of them can.
Okay.
See what goes.
I'll go to the next topic and then I'll come back to
Okay, yeah,
it.
definitely.
Okay. Hold on.
The largest one in the left side.
Like the new Doom game, like it's the guy like all in lava, like characters just always
So it's this one.
it was they take Dark's point of the predator trick players when you're moving down, you give it to the violence and smallest.
Because remember you want the smallest
And so
number.
they have like dynamic music, but like there's a matches.
Change it like the ones the smallest.
Like sound.
Cool. Okay. So I'm going to show you guys on the computer after how it sorts it online, but I can't show it on the computer right now because it's not working. So he's going to call the guy to come fix it. But while we do that, I'm just going to start with the heaps, and then we'll come back to it after we do heaps. I mean, after we do hash. Make sense? Okay. So for hash here, I'll let you guys try this question first, the number 6. Do I need to make it bigger? Yeah. Make it bigger.
Hey, there we go.
I saw like all of you squinting. I'm like,
So for these, do we plug in infinite any values, or does he want the one in between the sides of the table?
what do you mean?
So like modulo, like there's an infinite amount of numbers that would make it work.
Yeah, and exceed it.
But you just,
Yeah, so you're supposed to take these values here
Oh,
and
that's
input
right.
them into this table.
oh, so,
Good.
okay. Oh, you missed it.
So it says there, and is the table size. So if you look at the table.
Okay, sit next to the power button, right?
So there's 8. Okay. So that's
Yeah. Yeah.
Alright, this is my guess.
Press it twice. Or just once.
so yeah,
To the blue screen.
Yeah, that's what it is. Okay. Sorry, my sketch from shit.
It takes a second to do what you said. Alright.
It's not about zero. If they money, it's zero.
That's blue light with the
Anything
laptop.
modern
The one
zero is
closest
one.
to the button that switches.
By definition.
This is what you did before, right?
Hmm?
This is what you did before?
And
When we
Yeah.
went to the same.
because it's
If you can't, that's fine.
Alright, put it back in. Nothing's still working. No.
All right, that's
Yeah,
fine.
sorry about that.
You're good. Yeah,
Yeah. Sorry about that.
you're good. Okay. So for this one here, you want to insert these values using linear probing. So for the first one, you have 8, and you want to mod by the table size because this is the hash function that we have. So when you have 8 mod by 8, you're going to get 0. So you're going to put it in the 0 index. And then you're going to do 10, and 10 mod 8 is going to give you 2. So you try to put it here, but you would do in linear probing, you just keep going to the next index next to it. So if you try to put it here and it's not available, you'd go to the next one. So then you put 10 here.
Search left and right at the same time?
No, it just goes right.
No, it goes right.
Yeah, it just goes to greater than. And then for 16 mod 8 is also going to give you 0. So you try to put it here, but it wouldn't work, so you just keep going to the next one till you get to here. This gives you 16. So that's the easier one. And then for part B, you want to do these numbers using quadratic probing. So for 8, it would be the same. You'd get mod 0, and you would put it here, which would be the same. Let me get rid of these. And then you'd put in 22. 22 mod 8 is going to give you, I think, 6. Yeah, 6. So it would go here, but so with quadratic probing, you want to go to the position that was hashed plus Okay, for linear or quadratic? You said for quadratic? Oh. Okay, you're good. So for linear probing here, you would start by putting the 8 at the 0 position in the hash because 8 mod 8 is going to give you 0. That's to do for this hash. And then you try to input 10, and 10 mod 8 is going to give you 2. So you would try to put it here, but this spot is taken, so you'd go to the next one. And you would put 10 here into the 3. And then for 16, you would also, when you mod by 8, you'd get 0. So then you just keep going on to the next one. And then we got it here into 4. Okay. So then for part B, we're doing the same thing except with quadratic probing. And with quadratic probing, you go to the position, if the spot you hashed to is taken, you go to the position that was hashed plus n squared. So after so when we put 2 here and we try to hash to 6, it'll go to the position hashed, which is 6, plus n squared. So you start with 1. So you do 1 squared, so it would go to the next one and put it here. And then you would try to put 17 into the 1 position here, but that would not work because there's something here. So you'd go to the position hash plus 1 squared, which is 1. So you try to put it here, but this is also taken. So then you'd go to the position hash plus 2 squared. So you'd go to position hash, which was 1, and then you'd add 4. So 1, 2, 3, 4. So then go here. Yep.
What happens if all the positions are filled?
Then you would have to expand the hash table. You mean like if every single index was filled? Yeah, then you'd have to expand the hash table. Are there any other questions about hash? Okay.
Do we never start from index 0?
You said do we never?
We started at 0, was it 0 position?
Oh, well, if you add 0 squared, it's going to give you the same spot. So So like regardless of if you did or didn't, you would still be putting it in the same spot in the hash. What did you say? I couldn't hear. Right. Okay. So then we'll go on to the next one here, recurrence. Oh wait, I'll go back to the Minheap. Yeah. So to the Minheap here, I was mixing up with AVL trees when you delete from those. So with Minheaps, you just take it from you. It was when I took this. Let me just rewrite it somewhere else. So. $40, $28, 27, 30, 42 here. Yeah. So, where is it? Here. So for this one here, the problem I did last time, I took the largest member of the left subtree, which is something you do in AVL trees later. But so for this, instead, you just take the leftmost node, and so when you delete the 8, huh?
The last thing inserted?
What?
Does that just become like the last thing inserted?
Does what become the last thing inserted?
Like the leftist thing?
What do you mean?
No, never mind.
What? Yeah. Okay. Wait, did you have a question or?
I think I answered my own and I was wrong.
Okay. So in this case here, oh, there's supposed to be another node here. So say this was 47. So say you had this here, you would take this node here, and you would put this here. So then you have 47, 15, 28. There you go. So then this would be the one you had, and then you do the same thing before where you switch it with the, with the smaller two numbers, and then you'd switch it with this one here, and switch it with this. So then afterward you'd have 15, 28, 40. So then you end up with this after you did the two swaps.
One question.
Yeah.
Regarding when you use 42, because you said it was the rightmost in the left.
You mean this here?
Yeah.
No, yeah, that was not what you're supposed to do.
It was supposed to be the rightmost.
Right, I was supposed to take this one.
Oh, okay.
Yeah. That was the problem I had before, why when I did it at the end it wasn't complete. That was because I took the note that was here instead of taking the note that was here.
Oh, okay.
Make sense?
Can I see the thing again?
Left. Yeah.
It says after 2 deletions, you only did 1 deletion.
Okay, yeah. So then,
You would continue, right? You take out 15.
right,
Right.
right. So I'll do that here. So I'll take out the 15, and then you'd put the 40 here since this is the rightmost node. So then 40, 27, 30.
Will it always be the rightmost node?
Yeah, the rightmost node on the bottom.
So it's not leftmost?
Huh? No. Yeah. On Minheaps, it's the rightmost. The reason it was this one here is because it's the rightmost on the bottom level. So if these are the separate levels here, 47 was the only one on this level. That's why you did the 47. So to finish up this one here, 28, 47. So then you would just switch that with the smaller one here, the 27, and then you'd switch it with the 30. So then you'd get 27, 30, 40, 28, 47. Yeah, it's kind of like smushed up, but it's this one here. Did everybody follow that? Yep. Okay. Did I what?
You lost 42.
You lost the 42.
Oh,
So if it's the
sorry.
same or if it's smaller than, just
There. Okay. So then we'll go to the recurrence here.
I guess it chooses.
I had a quick question about,
Yeah, about the Minheaps.
yeah, for the new root, what if the two child nodes are the same?
In that, normally you don't allow duplicates into the Minheaps.
Okay.
Because then, like, if you had, if the duplicate values were the smallest number, then it wouldn't be a Minheap because there can only be one smallest number. You know?
How would the program know? Does it have to traverse through the whole heap to know that?
It depends on how you write the Minheap function itself. But like, so when you're inputting a value, say you, let me use this one here. So I'm going to use this one here. Say we wanted to input, I don't know, or this one isn't valid, so I have to go to this one here. Say we want to input another 30, right? So one way you could write it is if you were to try to put 30 here, you'd go down this here and put the 30. But when you were here, you'd see that you already had a 30. So you could do it like that. Or, like, there are different ways you can write it.
Like you can do like a post-order traversal to like
Right.
each level to see if it's.
Right, you can also just write a function that traverses the whole function to find if there's a duplicate or not.
So there's different ways, basically.
Right, right. Any other questions? Okay. So in this one here, we'll do the recurrence expression. I'll give you guys a few minutes to try this one. Or do you guys just want me to go over it? Okay. Okay. So for this here, you're going to, the basic concept is to use this formula I give you and keep inputting it into itself until you recognize a pattern. That way you can replace it and have a generalized expression. So for here, we'd start with t of n equals 2t. This is the expression they gave you, I just rewrote it. And then you would replace this t of n over 2 with, so if you have this equation here, t of n is this. That means that t of n over 2 is going to be equal to this same equation, but just inputting n over 2 everywhere you see n. So it'd be 2t n over 4 plus n over 2. Right. So do you guys get this part? What I did for here. So I took this equation he gave you where t of n is this equation here, and I just, everywhere you see n in this equation, I put n over 2 because we're trying to find t of n over 2. And that's how we got this equation here. And then since we have what this is here, we're just going to input that into this t of n over 2 here. So this is going to be equal to 2. And then we're just taking this equation here and putting it in here. 2t n over 4 plus n over 2. And then you just carry the plus n here. Does that make sense? Okay. So then just how we did here, how we know what t of n is, if we have t of n over 4, we know it's going to be 2t n over 8 plus n over 4, right? So you're going to take this equation here and substitute it in for the t of n over 4 that you have. 2, 2, t over 8 plus n over 4 plus n over 2 plus n. Right? So does that part make sense? Okay. Now I'm just going to the equation that way it gets less confusing. So for here, we just put this 2 into these two. T n over 8 plus n over 2. So the 2 plus n. Eight t n over 8. So it's going to be 2n. Right. So you see how this here, how we have 8t, this is our third iteration, and we did our second iteration here. What? Oh wait, no, this was our second. What happened? Did I lose an n?
Yeah, it's 3n.
Oh yeah. So where did I lose the n? N over 2. Oh, I lost in this step. Here. Okay. So in this is going to be plus 3n here. So in this case, you could do another iteration. Like you can do as many iterations as you want, but once you realize the pattern, you can just substitute in with k, where k is the iteration that you're on. So in this case here, the first time we had 2, and then we had 4 would have been our coefficient, and now it's 8. So you're multiplying it by 2 every time. So it's going to be 2 to the k t. And we had n over 4. We had n over 2, then n over 4, then n over 8. So it's going to be n over 2 to the k. And then plus, we had n, then 2, and then 3n. So it's going to be plus kn, where k is the iteration that we're on. And then this would be the final solution. But like if it wasn't clear to you on the third iteration, you could do a fourth one or a fifth one or however many you wanted to. Generally, you go at least 3 times though, because in this case, where you go 2 to 4, you don't know if you're multiplying by 2 every time, if you're adding 2 every time. Any questions on that or anything I did? No? Okay. So I'm going to have one more example of this. Wait, where's that? Here you go. So I have one more example of it just to, this is a topic that people generally are confused about, so I have extra examples of it. So you guys can try this one. I'm going to start doing this one here. So just to start off, I'm going to write what t of n over 2 is and what, t of n over 4 is, because we know we're going to have to substitute that in here. It's going to be t n over 16 plus n squared over 16. Right. This part makes sense here?
Should that be over 4?
It's n squared, so you square the top half and the bottom half. So the 4 would get squared to 16. So here we have t of n is equal to t of n over 4 plus n squared. And then t of n. So we're going to replace this part here with this equation that we got. N over 16. And then we have n over 16. So I'm going to write t of n over 16 here.
Should also need to add an n squared.
Hmm?
That second equation.
Yeah.
You said what should be n
N
squared?
squared on the end.
Oh.
Substitution.
Yeah, you're right. N squared here. So this is here. So then the t of n over 16 is going to be 64 plus they're going to be, okay, cool. That's 16 squared?
It is.
Okay. So then you just input this back into this equation again. So when you have the t of n over 16, that's going to turn into t of n over 64 plus n squared over 256. And then you have to carry these over. So plus n squared over 16 plus n squared. Right? So here we can figure out what the equation is going to be. So can we simplify this any?
It's a lot
We
easier
can.
to read if you leave them unsquared.
Yeah, like we could add these three together, but that would make it harder to read. So I'm going to do it this way. So we have t of n over, this is our third, this is our second. So this is going to be over 4 to the k. And then plus, wait, right. Yeah, we're going to do a summation for this one. Summation I equals 1 up until k, where it's going to be n squared over 16 to the k minus 1, if we have this here. So this summation pretty much does it count from I up until k, which is your iteration. So on the first iteration, you're going to add n squared over 16 to the k minus 1, which would be 0. So you'd get just plus n squared. That's how you get it for the first one. And then you're also on the second one, you're going to have that plus the n squared over 16. And then on the third iteration, it's going to be plus n squared over 16 squared, which would be 256. Does that make sense? Was anybody confused by the summation here? Or no? No? Okay. If there are no other questions, I'm going to go on to the next topic here, which is here. These are just different kind of definitions that you have to know. So how to convert from binary to hex and octal. Oh wait, this is supposed to be base 10 here. There you go. So I'll just give you like a minute or two to work it out if you haven't already, and then I'll go over it. Okay, so I'm going to start going over these here. So for a hexadecimal and octal, those are the more simple ones because you just separate each set of binary numbers. So for a hexadecimal, well, binary is base 2 and hex is base 16. And so 2 to the 4 is going to give you 16. So every 4 digits here, every 4 binary digits is going to be the same as 1 hexadecimal digit. So hexadecimal counts up from 0 to 16, 0 to 15. But instead of representing 10 as the number 10, that would get confusing whether you have the number 10 or 1, 0. So instead you go to A, and you count from 0 to 9, and then you go A through F. Yeah.
Is it always lowercase?
It can be upper or lowercase.
It can be upper or lower?
Yep. It's the same thing both ways, regardless of how you write it. So then 11 is going to be B, 12 is going to be C, 13 is going to be D, 14 is going to be E, and 15 is going to be F. There, right? So this here, using 4 binary values, so this is going to give you the largest hexadecimal value, which is going to be F. I'm going to write it from left to right. You can go from left to right if you want to. I'm just going to go from right to left. And this one here, you're going to add up these. So this digit here is going to be 1, this one's going to represent 2, and this one's going to represent 4. So you're going to have 4 plus 2 plus 1, which is 7. So you'd write 7, so that'd be for that one. And then for this one here, you'd also separate it. And the 2 values are the same thing. So this would represent the 1. This would represent the 8. So this would represent the 4. So you add the 4 and the 1, and that would give you 5. So this would give you 5, 5. And then this one here. These two are also the same. So this one's going to represent 8, 4, and 2. So when you add 8, 4, and 2, you're going to get 14, which is E. So you're going to write E, E. And then this one here, we found out that this one was F already. And, oh wow. And then for this one here, this is going to be 4. So you have 4F. Yeah. This goes by powers of 2. So this is going to be the 0th power of 2, which gives you 1. This is going to be the first power of 2, which gives you 2, and then 4, 8. And if there are more, it goes 16, 32. So then here, so we're going to do octal. Octal is the same way that hex is 2 to the 4. Octal is 2 to the 3rd. We'll give you 8. So instead of separating them in sets of 4, you separate them in sets of 3. So this one here. And this is a set of 8 digits, so you would just put like a 0 here to make it even. That way it's sets of 3. So we'll start at this one here. When you have the 3 1s, that is the largest value you can represent in octal, so that's going to be 7. Octal is base 8 here, so you can only represent the numbers 0 through 7. So the highest is going to be 7 here. And then you're going to have 3 more ones, which is also going to give you 7. And then you're going to have 0, 0, 1. which is going to give you just 1. So it's 177. And then for this one here, this part is the same, so it's going to give you 1. This one here is going to give you 2. And this one here is going to give you 5. Any questions about this so far? Or no? Okay. I'm going to go through these. So this one's going to give you 3. This one's going to give you 5. And the last one's going to give you, wait, this one's going to be 4. This is going to be 3, 4, 5. And then the last one here, when you separate it, you're going to get 1, another 1, and then 7. So these are here. So decimal is the one that's not as simple because you can't just separate it in sets of 3. You have to actually multiply these out here. So I'm going to use, I have another paper.
Would it be 3, 5, 6?
What'd you say?
The third one?
Third one? No, it's going to be 3, 4, 5 because you separate it in sets of 3 here. So this one here is 3. This one here, this is the 1. This is going to be 2, and this is going to be 4. Oh yeah, so that is going to be 5. Yeah, 3, 5, 6. So this one's going to be 4. This one's going to be 2. So you add those 2, you're going to get 6. 3, 5, 6. So then it's going to get really messy if I write it on here, so I have another paper. I'm just going to put it on here. So here. So then for decimal, each of these, this is going to represent 2 to the 0, 2 to the 1, 2 to the 2, and so on. So for this one, this is going to be 1 plus 2 plus 3, wait, no, plus 4. And then this one's going to be plus 8. This one's going to be plus 16. This one's going to be plus 32. And this one here is going to be plus 64. And then you just add all of these together to get the decimal value. Let me see. I don't know. Does somebody want to do that out so we can? What did you say? Yeah. 127? Okay. So that'd be for the decimal for that one. For this one here, you're going to do the same thing, except all the ones where there are zeros, you're going to ignore it. This is going to be the 1 plus, you're going to skip the 2 here and go to the 4. And then you're going to skip the 8 and get the 16. And then you're going to skip the 32 and get the 64. And then you're going to add all of these together. And that'll give you 80, 85. And then this one here. Do you guys want me to go through the other two, or do you think you got the concept? Do you know? No? Okay. Okay. Same. Go to the, where's the last paper? Oh. Okay. So here. Oh wait, let me use this one. This one is written darker. There you go. So you're converting, this is going backwards from decimal to all the other hex, octal, and binary. So in this one here, it's easiest to just convert these to binary and then convert from binary to octal to hex. So for each of these, to convert from a decimal to a binary, you want to divide by multiples of 2. So you're going to do 63 divided by 2. That is going to give you 31 with a remainder of 1. And then you're going to do 31 divided by 2, which will give you 15 with a remainder of 1. And then 15 divided by 2 gives you 7 remainder 1. 7 divided by 2 gives you 3 remainder 1. And then 3 divided by 2 gives you 1 remainder 1. And then for the last one, what do I have? 1 divided by 2 gives you 0 remainder 1 here. And then this would be your binary here. And if you want to write in 8 digits, just do 0, 0, 1, 1, 1, 1, 1, 1. Make sense?
How'd you get the 2 zeros?
2 0. Oh, you just have the 6 ones here. I just wanted to make it 8 digits. You could just not have these, but I just wanted to keep it consistent and have it 8 digits. Yep.
The same process work if you divide by 8 and 16 on the hexagonal.
Yes, you could do it that way, with just putting the remainder as the value there. Okay. So then we're going to do for 32 here. 32 is simpler. You do 32 divided by 2, which gives you 16, remainder 0. 16 divided by 2, 8 divided by 2, 4 divided by 2, 2 divided by 2. Give you 8, 4, 2, 1, and then 1 divided by 2, 0, remainder 1. Here. See here? Okay. So for this one here, I didn't say for this one, but you always start from the bottom and go up. So in this case, it would be 1 with 5 zeros. 2, 3, 4, 5. Wait, 1, 2, 3. Yeah. And then I'll just add the 2 zeros at the front to make it 8 digits. Any questions on that so far? Yep.
2 to the 6 is 64.
You said 2 to the 6th. So this would be 1, 2, 4, 8, 16, 32. What? Oh, you start at 2 to the 0. So the 6 digits here, this is 2 to the 0, this is 2 to the 1, 2, 3, 4, 5. That makes sense?
Yep.
Cool. So then we'll just go through the other two. 37 divided by 2, going to give you 16, 17. It's going to be 18, remainder 1. 18 divided by 2, going to give you 9, remainder 0. 9 divided by 2 gives you 4, remainder 1. 4 divided by 2 gives you 2, remainder 0. 2 divided by 2 gives you 1, remainder 0. And 1 divided by 2 gives you 1, remainder 1. So then you just read it back this way. And you get 1, 0, 0, 1, 0, 1. That make sense? Gonna add these two there. And then I'll do 27 here. 27 divided by 2 is going to give you 13, remainder 1. 13 divided by 2 is going to give you 6, remainder 1. 6 divided by 2 gives you 3, remainder 0. 3 divided by 2 gives you 1, remainder 1. And 1 divided by 2 gives you 1, remainder 1. So you have 1, 1, 0, 1, 1. And I'll just add the 3 zeros to make it 8 digits. Make sense? And then this is the same thing as before, how you're converting from binary to octal to hex. So do you guys want me to do that or no? No? Okay. So then here, we're going to go on to the next topic, which is just bitwise shifts. So I'll give you like 30 seconds, I guess, to do these. These shouldn't take very long. Okay, so for this one here, you're just going to shift left twice. And anytime you shift left, you bring in zeros here. So you would just start writing from here, 1, 1, 1, 1, 1, 1 with 2 zeros on the right. This one here, when you're shifting right, when you're shifting, does it say with unsigned? Okay. So I'm going to assume these are signed values because it doesn't say it's unsigned. So if you shift left, you have to look at the most significant digits to see if it's a 0 or a 1. If it's a 0, you treat it just like a left shift and just shift in zeros. So in this case, you would have 0, 0, 1, 0, 1, 0, 1, 0. 1, 2, 3, 4, 5, 6, 7. Yeah. So in this case here, you're also shifting left, so you would just shift in zeros. So you just do 0, 1, 1, 1, 0, and then 2, 3. And then this one where you shift left, but you have to take into consideration the sign bit. So if there is a 1 here, and you're shifting right, then you have to shift in ones instead of shifting in zeros. So in this case. So I would ignore these 4, and I would just write the 0, 0, 1, 1, and then you'd shift in the 4 ones. Yep.
So in the test, if we have a question like this, it's going to say that it is signed?
It would say whether it's signed or unsigned. And if it's unsigned, you treat them both. You always shift in, yeah. If it's a signed number, then you have to take this part into consideration, the signed bit. Yep.
How do you determine if they were signed or unsigned based on the binary?
No, they will tell you if it's signed or unsigned.
Okay.
Yeah, I just assumed in this case it was signed.
Just how clear is that?
Right, right. Any other questions on this? This one? Yeah, okay. So when you have 1, 1, 0, 0, 1, 1, 1, 1, anytime, let's say we're going to shift right once first, you take into consideration the most significant bit, since that would be the signed bit. You know how when you have a 2's complement number, the most significant digit is a signed bit, it just tells you whether it's positive or negative. So I'm assuming this is a signed bit, which tells me that the number is negative. So in order to keep the number negative when I shift it, you have to shift in ones. So when I shift this right, I would shift it with a 1. Does that make sense?
If you're shifting 2's complement to the left, you still add 0, right?
If you're shifting it this way?
Yeah.
Yeah, you still shift in zeros, even if this digit is 1.
Okay.
Yep.
Yeah, if it's
So if it's signed, you shift into the right, and it's otherwise
Right.
1, and then you add an 1, and 0, you add a 0.
So that's the only caveat, you're shifting to the right and side.
Right. One thing you can actually test is with C. It has 2 different, like when you're shifting left, it has only one way to shift left. Like if you do this in C, it'll do one thing. But this and this mean 2 different things in C, whether you have 2 or 3 arrows. But there's only one shift, there's only one set here. This doesn't exist because it does the same thing as this. Because when you're shifting left, it doesn't matter if it's a signed bit or an unsigned bit.
Both for sign.
Right. That makes sense? Yeah. I mean, he probably won't ask you that, but I just thought it was interesting.
That's going to be like a foundation exam somehow.
Okay. So I'm going to the next one here, which just AND or an XOR. So yeah. With this, you literally just look at the 2 sets of bits. So if both bits are 1, then you're going to have a 1. If both aren't 1, or if either of them aren't 1, then you're going to have a 0. So in this one, you have a 0 here. So when you AND them, you're going to get 0. In both of these, you also have a 0, so you're going to get 0 for these. In this part here, they're both 1s, so you bring a 1. In these 4 here, you have 0, 0, and 2 1s. Everybody get that part? Okay. No?
Say it one more time.
Okay. So when you're ANDing 2 values, A and B, you take each bit individually, and you check to make sure they're both 1. So if both of the bits are 1, then you're going to end up with 1 as a result. If either of them are not 1, then you're going to end up with a 0. Make sense? Okay. So I'm just going to do these quickly here. 1, 0, 1, 0, 0. And this one here, you have a 0 here, so you're going to have a 0. You bring down the 1. You're going to have zeros for these, 1s and 0s. And these two here, you're going to have 0, 0, 0, 0, 0, 1, 0, 1. Okay. Any question on the AND part? Okay. So OR is going to be the opposite of AND, where if either one of them is 1, you're going to have 1 in the result. So in this case here, you have a 1 in B, so you have a 1. You have a 1 in A for these, so you're going to have 1s for these. And you also have a 1 for these here, so you're going to have 1. So in this case, all of them are going to be 1, if you OR those two.
Could you explain that one more time?
Okay. So you take each individual bit separately, and if either one of them is a 1, then you're going to have 1 in the result. If both of them are 1, you're also going to have 1 in the result. So as long as at least one of them has 1, then you're going to have a 1 in the result. And I'm just going to do the same thing for these. It's going to be 1s. Both of these do 0, so you're going to have 0 here. You're going to have a 1, 1, 1, 0, 1. You have 1, 1, 1, 0, 1, 1, 1, 0. 0, 1, 1, 1, 1, 1, 1. Okay. So XOR is, the X stands for exclusive, so it's exclusive OR. So if both of them are 0 or both of them are 1, you're going to get 0 for the result. So this XOR here means one and not the other. So you know how if you have this, in this, if you're doing regular OR for this, both of these are going to give you 1. But if you're doing XOR with these, this is going to give you 1, but this is going to give you 0. Because both of them can't be 1. If both of them are 1, you're going to get 0 when you're doing XOR. Does that make sense? Okay, so I'm going to do an example for this one here. I'm going to write it on the new paper. That way it's easier to read. Yeah. So this part here, you have a 0 and a 1, so you're going to have 1, 1, 1. Both of these are 1, so you're going to have 0. These two, you're going to have 1s, and both of these are 1, so you're going to have 0s. And then we're going to keep doing these. 1, 0, 0, 0, 1, 1, wait. 1, 0, 0, 0, 1, 0, 0, 1. 1, 0, 1, 0, 0, 0, 0, 1, 0. And then 0, 1, 1, 1, 1, 0, 0. Okay. So does anybody have any questions about AND or XOR? No? Okay. I'm just going to go over some things about binary trees that he may ask you on the test. I left this part for last because I'm not sure if it'll be on the exam, but it might be, so I have this here. So these are just notes on binary trees in general. We went over what complete was already with Minheaps, how you have to fill it up from left to right. But full is when every node has 0 or 2. So if any node has 1 child, then it's not going to be a full tree. These are just definitions that he might ask you on the exam. So a perfect tree is where all of them have 2 children except for the leaf nodes here. Make sense? Okay. I can. Yeah. So it'll be on the same website. So
Your website or the study?
I'll post it on both. So if you go to ucfstudyunion.wordpress.com, I'll post it on there right after the session, and then also on my regular UCF.
The website that was like in the announcements when I posted for this, is that?
No, that's a different one. The one he posted just has the schedule. So I have it here. I have it written. Oops. Where did I put it? Oh, it's on the front page of here. That's that. Here you go. So it's right up here. That's the website there. Yeah. So you can either go to this website to find it, or I'll also post it on my regular one. Yep.
I know it's mostly concepts, but should we know how to code it too? Like,
You mean like how to code up AVL trees and stuff?
Or anything?
No. AVL trees are one of like the, it's actually really complicated to actually code up. So like if he asks you on the exam, it would probably take you like over 30 minutes to do. So I highly doubt he will ask you to code it up. It'll probably be mostly he'll give you like pieces of code and ask you what the output would be, or he'll like give you drawings of heaps or AVL trees and ask you what it would look like after they rotate or stuff like that.
For the final exam, it's safe to say that we don't have to worry about learning how to code.
He might ask you to code things, but it's just not going to be like code AVL trees. Yeah.
What about me?
Huh?
What about Minheaps and trying?
Oh no, he's not going to ask you to code those up either. He's not going to ask you to like code up entire algorithms. If he asks you to code things, he'll give you like pieces of code and he'll ask you to like fill in parts to ask you. Yeah.
Talking about code, do you know like what code you might ask?
One thing he might ask that's like reasonable would be like hash. Cause like he'll ask you to write a function that does quadratic probing in a hash. Right. So you just take whatever the hash value is and add n squared, and you just keep increasing until you find.
You have the array, you've taken the value, modded, and then inserted, but if it's full, then
Right. I haven't like seen the test or anything, so this is just like what I would think based on like what he's giving you on other tests. Huh? Wait, what was the question? I don't. Okay.
I'm just gonna ask if you will be able to see the test.
I'll be able to see like he'll show me the test that he gives you. Yeah.
After?
No, after. Definitely after. No.
So did he give you this study guide, or did you create this on your own?
No, I created this. Yeah. I just went back to his notes and went based on what he said would be on the exam. Okay. What was I looking at? Where is this? Okay. So for here, these are examples here. Hold on. I'm going to draw a few of these and have you tell me whether or not they are complete, perfect, or perfect. Did you guys have any other question about anything else for the exam? Oh. Okay. Well, if that's it, then we are done. Good. If you guys want to come up and take pictures of anything, you can, or...
Dude, you're posting this online, right? Including this slide?
Huh? Yeah.
Okay.
Yep.
Where are you posting it to? An announcement? Or?
Right. Where is it? To ucfstudyunion.wordpress.com.
Okay.
It's right here. Right here at the top. Yep.
Can I see the page with the binary conversions?
Yeah. Binary conversions here. Yep.
I just need to take a picture too. That's
Okay.
because I wasn't here the whole time.
Yep.
So I know this is what he posted today, Professor.
Okay.
And for the operation, like this is what he got. This is the answer. So that was the same
Which
question.
one? Okay, I was doing this one as if it was signed.
Oh, if it was signed.
Yeah, if it was signed. He didn't specify whether it was signed or unsigned.
Okay, so if it's not signed, then you
Right.
just do this.
Right. If it was signed, then you would shift in ones.
Shift in ones.
Right. No, not for this one. If there was a, you see how, I'll show you on mine. On mine, I changed that first bit there to a 1.
The first one?
Yeah.
Okay, so it's 11001111.
Right. That's
so
what,
because you shifted right,
right.
it would be.
If it's a sign value, then you have to keep the sign. You know how when you have a sign, like in 2's complement, the most significant digit tells you whether it's positive or negative?
So say, for example, if you're shifting right and you have that 1 on
Right.
the left, you have to make sure you put that 1 back. You have
Right.
to make sure it's a 1
No,
at
no,
the end.
every number you shift in is going to be 1. So say you shift left, say you have, can I write on here?
Yeah, go ahead.
Okay. So you have 1, 0, 0, 0, 0, 1, and you want to shift this right twice. On the first shift, these are going to stay here, and you're going to shift in a 1. And then that would be 1 shift. And then after the second shift, you would shift in another 1. So you'd have,
Oh, so with sign, you're going 1 at a time.
right. That's if this is signed. If this is unsigned, then you still just put zeros here.
And
And this rule applied to if it's signed, this applies to right or left shifts, right?
it only
No, only right shift.
Only right shifts.
Right. Because when you're shifting left, this isn't a signed bit. This is just a regular number.
Gotcha.
So you still shift in
It's
zeros.
the same if like you need to keep like a 0, like you add zeros.
Yeah.
If it was that sign.
Yeah. If it's not signed, then you shift in zeros no matter what.
Okay, and one more question.
Yep.
I still don't get this one.
So when you said numbers, that's how you know. Okay.
Because if
This one.
This one? Oh, the quadratic programming?
Yeah.
Okay. So, say